Welcome back to the 13th video about the Melexis MLX90363 Triaxis magnetometer. In the previous video, we successfully uncovered the secrets of the sensitivity mismatch parameters and admittedly got stuck on the FHYST parameter. Its behavior didn't make any sense. We will have to revisit that at a later time. Card here, link in the description. In this video, we will start out with the remaining orthogonality parameter, and then we'll see. Enjoy! Just a quick recap about the orthogonality parameters, or phase error correction parameters. In the 11th video, we covered the orthXY and the orthSelect parameter, and we weren't able to see any effect of that orthXY parameter because it's there to correct an angle error of 0.3 degrees between the X and the Y sensor. We couldn't measure its effect. Anyway, what we haven't tested so far is the orthB1, B2 parameter, which will kick in if we choose orthSelect to be 1 instead of 0. And with the reverse engineering, forward engineering, we introduced in the previous video, we really should be able to figure out what that does. According to the block diagram of the digital signal processing, orthB1, B2 is multiplied with the B2 channel, which is really by default the Y channel, and then the result is multiplied with the B1 channel, which is by default the X channel. So the question arises, is that really true? And what's the scale of the orthB1, B2 parameter? According to the overview table, orthB1, B2 is an 8-bit value and it defaults to 0, which is a bit odd. Because B2 times 0 is 0. And B1 times 0 is also 0. So the default value would result in the B1 channel always be 0. The only other information about orthB1, B2 is given in chapter 16.3.2, magnetic angle XZ and YZ, so in 3D mode. And there it says again, okay, 8-bit parameter, and range between 0 and 2 translated into a float, a typical 0. And that was the formula we just saw in the block diagram. However, another formula is given here saying B2 is equal B1 minus B2 times orthB1, B2 divided by 1024, which, if orthB1, B2 is an 8-bit value, so 255 at max, would put it into a float range between 0 and almost 0.25. Yeah. So with all that uncertainty, let's dive right into the experiments and change some parameters in our setup. As always, I keep the virtual gain fixed at 5 and then I set orthSelect to B1, B2 and I set the raw B1, B2 value to 0. Let's have a look at the plotter. And as expected, we see nothing. So both our own calculation and the angle return for the chip seem to be the same. Let's stop that for a second right here. Yeah. There is no real difference, as expected. Now turn up that orthB1, 2 parameter to 255. With B1, B2 raw set to the maximum, 255, and that correction be intended to correct orthogonality errors of up to 10 degrees, we should see something. And at a first glance, we see nothing again. Like with that BXY. Let me stop that somewhere, maybe about here. Oops, sorry. Turn the motor off. Here. Nothing. So it absolutely makes no sense to dive deeper into that thing because, yeah, we cannot observe any noticeable effect. Also, having a second look at that formula here given in 16.3.2, I noticed it's like the formula given in the block diagram BS. Let's assume for a moment we set auth B1, B2 to 0. Then B2 times 0 is of course 0, and we subtract 0 from B1. Meaning B2 is simply set to B1. Now B1 and B2 carry exactly the same signal, and you can't possibly calculate an angle from that. And even if auth B1, B2 is set to 255 and this term is near 0.25, then B2 is 3/4 B1 and 1/4 B2. Yeah, it doesn't matter how you look at that, it doesn't make sense. So let's move on to hopefully greener pastures and have a look at the filter parameter, enabling of signal filter, which is simply 2 bits. That parameter is explained in unusual detail in chapter 16.5. Basically, the chip implements a finite impulse response filter, and you can preset 4 different filter settings. That is setting 0, bit pattern 00 means there is no filter. And they give you the coefficients here, 6 in total, that are used in that formula depending on the filter setting. They call it some names, and I used these names in the enums to set that configuration option. And they even give you the 90% response time. That is in samples, not some real time, but in samples. Meaning if the filter is off, you get a 90% response after just one sample. Well, in fact, you get a 100% response if there's no filter after one sample. Filter setting 1, you need 2 samples until you're approaching 90% of the signal again. 4 samples, 5 samples for the medium, strongest filter setting. And they also give you a filter RMS efficiency in decibels. So the maximum filter should take out about 6.6 decibels from the noise that is on the signal. So let's test the filter. Again, in the setup, I first resetted the auth parameters to their default values, and then I have still virtual gain fixed to 5, and then I have here my 4 update filter statements, starting with no filter, the extra light filter, the light filter, and the medium filter. Yeah, you could rename them, but then it would diverge from what it's written in the datasheet. Not that that's any worth, but anyway. So let's start with the no filter, which is the default. And to visualize the noise, I'm only printing out the x-axis and then a min and a max line on the serial plotter. So the loop does still the same, but I'm just printing out x and then -5 and 5 as minimum maximum lines. This time we don't need to film our little chip there with a rotating magnet. I carefully rotated the magnet until we are centered around the 0 line. And with no filter, you can see we have currently, here is 3, a noise level of a maximum. Oh, there was a higher peak, but let's say ±3 least significant bits. Now I will change the filter setting to very light and we'll have a look again. So we're looking now at the same signal with very light filter. And yeah, you can see a difference. You know, the high spikes are ±3 or, well, there was a single one, okay, but they were more frequent. We are now at about peak ±2 LSBs. So yeah, that actually does seem to work. And here's the same picture with the filter setting light. And yeah, you can see we are basically down. Yeah, sometimes there are some peaks, but yeah, like there. But we're basically down to ±1 LSB noise with a odd 2 LSB peak. And here's the medium filter setting. So the maximum setting we can have on the filter, but it's called medium. Not a great difference to the light filter. But remember, according to the datasheet, the light filter has 6 dBs and the medium filter has 6.6 dBs. Yeah, no filter obviously has 0 dBs and the extra light filter has 3 dBs. Yeah, so you can basically set 0 dBs, 3 dBs, 6 dBs and 6.6 dBs. Why they did that, I don't know. I would have chosen 0, 3, 6, 9 or 0, 3, 6, 12 dBs. Something, you know, sensible. But that last step between light and medium from 6 dBs to 6.6 dBs, yeah, well, I stopped wondering a long time ago. But it works. Okay, that was the filter parameter. And besides the 3D parameters, which are 3D, KALPHA, KBETA and KT, there's just pin filter, user ID and free left, which really don't influence the digital signal processing. If you want to know more about these parameters again, watch the video where we read out the configuration, card here, link in the description, and the video where we wrote the configuration. There we at least wrote user ID as an example. Card here, link in the description. So the next step would be to set our parameter 3D to 1 or true, and then we can have 3D angle readings, an alpha and a beta angle according to these formulas. But I won't go into the details in this video. Yeah. We have first to understand these formulas here. This is just a preview. And we really have to understand these formulas before we can do anything with the KALPHA, KBETA and KT parameters. Because, yeah, that's the only other information given about them and what they do. So basically 16-bit values in a, well, assumed range according to the datasheet between 0 and two with some typical values. And please note, these typical values are other typical values than given in the application note. Oh, well. And at one point, I really want to revisit that of B1, B2 parameter, because I mean that they put wrong information and typos and stuff into the datasheet. It is what it is. However, that they describe a functionality here that's not there, this would be bit outrageous, wouldn't it be? And I have a theory that the auth B1, B2 parameter is not only dependent on 3D being 0, but also maybe on that map XYZ parameter we just, because it's self-explanatory, just skipped over. So maybe that auth B1, B2 with auth select being 1 is only applied with certain settings of the map XYZ. But I'll have to do some research before we dive into that. That's it for today. A rather short video about our little magnetic sensor chip, but before we start with that new chapter with 3D measurements, we need to lay some foundations about the math and the geometry and stuff. Anyway, till next time, bye.